Hi, and welcome to Lecture 9, in which we're going to continue our exploration of Lagrangian mechanics. In this lecture, we're going to talk about a number of concepts related to one single theme, which is that Lagrangian mechanics allows us to really carefully choose which coordinates we use to do our problem. We discussed generalized coordinates last time, and we're going to push that idea further this time. To start out with, last time we talked about general coordinates as being the coordinates on a constraint subspace, the space of allowed places that the system can be, or allowed states that the system can be in. In this case, or in today's lecture, we'll talk about generalized coordinates a little bit more generally. So I'm going to give a more careful definition here. Generalized coordinates are any coordinates and we'll call them Q1 through Qn, such that the system's state can be fully specified using Q1 through Qn and Q1 dot through Qn dot, and possibly T. Now, of course, if we have a system which is constrained to be, for instance, in some subspace of the whole coordinate region, then we can use some generalized coordinates to specify points on that subspace. But we can also use different sets of generalized coordinates in any space. So a great example is in R3 that we can use spherical coordinates rather than rectangular coordinates. Okay, so here's an example. We'll do spherical coordinates for a mass on a spring in 3D. Okay, so we'll attach a mass m by a spring with spring constant k and equilibrium length 0 to the origin. All right. Now, what we would have for the Lagrangian in rectangular, let me be specific here. Well, in this case, our generalized coordinates are just rectangular coordinates, x, y, z. And our Lagrangian would be the kinetic part, 1/2 mx dot squared plus y dot squared plus z dot squared minus the potential part, minus 1/2 k times x squared plus y squared plus z squared. But we can rewrite this using spherical coordinates. Now, the rules for rewriting in terms of another generalized coordinate system are exactly the rules that we discussed last time for a constraint subspace. We're just going to rewrite this thing, this object, by rewriting each of the variables on the right-hand side in the new generalized coordinates. And this seems like it would be quite challenging in general, but we've already worked everything out for spherical coordinates. So I'll just jump right to the result. So we get an r dot squared plus an r squared theta dot squared plus an r squared sine squared theta times phi dot squared. Then minus 1/2 k. We'll notice that x squared plus y squared plus z squared is just r squared. Great. Okay. Now we're going to come back to this example a little bit later. All I'm trying to illustrate here is that in spherical as well as in rectangular, we can write our Lagrangian in exactly the form that I've specified over here. We can write the Lagrangian in terms of our coordinates and their first derivatives. Here, we'll get r dot, theta dot, and phi dot, and also some combinations of r and theta in the kinetic term, and then we'll get r squared down here. Whereas up here, we'll get some different combination. But in either case, we can describe the Lagrangian in terms only of the coordinates and their first derivatives. Now, with generalized coordinates, we can do some really interesting things. In particular, notice that we can also let these depend on t. This is also going to be the way that we deal with magnetic fields. Now, I'm going to jump to the computer and do a couple more examples to illustrate those things, and then I'll be back here later.
So let's give a first example. And just to keep it really simple, let's talk about a free particle in 2D. But whereas in the past, we've of course done this in rectangular coordinates because that's the way that makes the most sense, let's do it in polar coordinates. This is a little bit silly, but it at least demonstrates that it's possible. Okay, so recall that we know that the equation for a free particle is going to be Newton's second law equation will be mr double dot is equal to 0. Okay, and that's the 0 vector. Well, let's describe the Lagrangian. The Lagrangian is just going to be the kinetic energy in this case, which is 1/2 mv squared. Okay, so then the Lagrangian with our trajectory applied, let's call it u as we've done in the past, u dot is equal to 1/2 mu dot u dot. All right, and here's where I want to take things to polar. So let's re-express u dot in terms of polar coordinates and unit vectors. We can do that over here. All right, so recall that u is going to be equal to u times r hat, no problem, where u is our distance from the origin in polar coordinates. So this is distance from the origin. And let me actually just in general give our trajectory is going to be r equals u. And then phi equals going to need to come up with something else for this. Let's say alpha. Okay, so now u dot, we'll remember, is u dot r hat plus u r hat dot. But r hat dot was given by phi dot phi hat, and since phi dot is alpha dot here, we'll say alpha dot phi hat. Great. Okay, so I'm just going to plug that in here. 1/2 m. So I'm going to get 2 parts. Because r hat and phi hat are orthogonal to each other, I just square this coefficient and then square this coefficient. So I get u dot squared plus u squared alpha dot squared. Good. Okay. Now I can go right to using my Euler-Lagrange equations. Here I'll have one for alpha and one for u. Or one, yeah, that's right. Okay, so dl du is equal to, well, I get my mu alpha dot squared. And dl du dot is just mu dot. So my u Euler-Lagrange equation is mu double dot is equal to, mu alpha dot squared. Good. Now for my alpha equation, dl d alpha, well, that's 0. And dl d alpha dot is mu squared alpha dot. Now this equation gives me that mu squared alpha dot is equal to a constant. Let's give that constant a name. Let's call it little l. And I'm going to use that to solve for alpha dot in terms of this stuff. Okay, so the implication is that alpha dot is equal to L over mu squared. We're actually seeing a little hint of what's coming a little bit later. Okay, now what I'm going to do is take this equation and loop it into here. So what I get in the end is mu double dot is equal to mu L squared over m squared u to the fourth. Or after doing all my cancellations, I'll get L squared over mu cubed. Good. Okay, so let me rewrite this just to put u on one side. I'll get L squared over m squared u cubed. Now, the next thing I want to show with generalized coordinates is that we can deal with generalized coordinates and with holonomic constraints, even if our constraints are time dependent. Time dependent constraints. All right, so if we have time dependent constraints, remember that our constraint equation was something like k of r equals 0. Now we'll let it be k of r and t equals 0. And once again, I want to work through this by working through an example. So we'll have a hoop here in three-dimensional space. And on the hoop, there's a bead. Let's say the bead has mass m. The bead can move up and down on the hoop, so it can sort of move back and forth, but it can't leave the hoop. And importantly, the hoop is spinning. The hoop is rotating around the z-axis with an angular frequency omega. Good. Okay, so this suggests what our constraint should be. And we might as well write it in cylindrical coordinates. So let's say we have kind of two parts of our constraint. In fact, we have two constraint equations. So k1 of RT equals 0 and k2 of RT is equal to 0. k1 of RT is equal to 0. Let's let that be our easy constraint. The plane of our bead must always be the one that has rotated by an angle omega times t, which means that our phi coordinate is always going to be omega t. Now, even though I've been using u and alpha and other constants like this, this isn't usually what references do. They use ordinary coordinates, r, x, y, z, etc. And I think at this point, it's probably a good idea for me to make that switch as well, just to match what references are doing a little bit more accurately. So I'm going to use rho, phi, and z here as our coordinates. And you'll just have to remember here that I'm sort of using them for double duty. They mean either the coordinates themselves or the specific trajectory of our object. Okay, without further ado, let's write down what this is. So we have that phi is equal to omega t. So we should make our constraint, which we want to be equal to 0, phi minus omega t. Great. Our second constraint is the one that makes us constrained to the bead. So that's that the square root of the rho coordinate, that's our cylindrical radial coordinate. plus squared plus z squared must be equal to, well, we need to give this some radius r. And I shouldn't say equals, I should say minus. Now, we haven't dealt with a case where we have two separate constraints before. As long as our constraint subspace is nicely behaved, it's all right if we have multiple constraint equations. And in this case, we're totally fine. We have two constraints in three-dimensional space, which constrains us to a one-dimensional space, and we're okay. Well, now that we've given our constraints, it's a good idea to pick our generalized coordinates. And I think it's relatively obvious what we should pick here. It's the angle that the bead forms between the negative z-axis and itself. So let's call this parameter theta to keep it separate from phi, to make sure that we're not confusing them. All right. Now what we need to do is rewrite rho, phi, and z in terms of our generalized coordinates. Phi is easy because that doesn't depend on our generalized coordinate at all. It's just omega t. On the other hand, rho is equal to r times what? So that one is, if this is theta, then that's our rho coordinate. And that is the sine of phi, or of theta, sorry about that. And lastly, we have z, which is minus r times the cosine of theta, because we're going to let this be the z equals 0 point. Great. Now, while we're at it, we might as well express r dot theta, phi dot, and z dot. So r dot is equal to, well, r is a constant, so it's going to be r theta dot cos theta. For phi dot, we just get omega. And for z dot, we get, well, that one is going to be r theta dot sine theta. Good. Now, to figure out our Lagrangian, we need to write down t and u. U is the easy one. U of r is just mgz. So that gives us mg r cos theta, with a minus sign, sorry. For t, that's a little bit harder. T of v is 1/2 mv squared. And that's going to require us to remember what our vector dot is in cylindrical coordinates. Okay, so r in cylindrical coordinates is equal to rho hat plus z hat. Which means that r dot in cylindrical coordinates is going to be what r dot is in polar coordinates, and then plus z dot z hat. Now, we already worked this out in this video, so I'm just going to refer you back up the video if you want to see this again. What we get is rho dot rho hat plus rho phi dot times phi hat plus z dot z hat. And the reason, remember, that works is that the z hat vector is constant over time. Okay? So this is now in cylindrical coordinates, I should say, 1/2 m times rho dot squared plus rho squared phi dot squared plus z dot squared. Okay, now for our specific case, I want to rewrite all of these in terms of our generalized coordinate theta. So I get 1/2 m. Now I get rho dot squared, which is exactly r squared theta dot squared cos squared of theta, plus r squared phi dot, or rho squared, phi dot squared, which is r squared sine squared theta times omega squared. And then lastly, I have plus z dot squared, which is r squared theta dot squared sine squared theta. And for good measure, let's use our Pythagorean identity on these two terms. So we get 1/2 m r squared theta dot squared plus r squared omega squared sine squared of theta. Great. Now we're ready to go. We just plug this right into our Lagrangian. So So our Lagrangian is 1/2 m r squared. I can even pull the r squared out. Theta dot squared plus omega squared sine squared theta minus, except that minus combines here, so plus mgr cos theta. Okay, ready to go. dl d theta. Well, I need to do something with this sine squared, so I'll get the 2 canceling that half here. And then, after I do that, I need to use the chain rule to give me cos theta. Good. Then I have a second term, which is minus mgr sine theta. Great. For dl d theta dot, I get, well, mr squared theta dot. No problem. Okay, let's combine these together to get my Euler-Lagrange equation. So I get mr squared theta double dot is equal to mr squared omega squared sine theta cos theta minus mgr sine theta. Or if you want, I can group some of these terms. So I can, for instance, pull out an m and an r and a sine theta. And what's left over is r omega squared cos theta for the first term minus g. Good. And if I wanted to kind of get some intuition, where are these terms coming from? Well, this is the force of gravity. And it's weird. It depends on theta here, which seems a little bit strange. But the reason that it depends on theta is, remember that there's a normal force from the hoop that is to some degree opposing the force of gravity. So even though we didn't write down our forces of constraint, they are there sort of canceling out part of the forces that we expect. This second force is a force that you may have encountered in intro, and we will be talking about pretty soon. This is a centrifugal force. Great. Okay, so we can deal with time-dependent constraints. That's pretty cool. Now, we've given one example with magnetism, but I thought it would be a good time to do another one right now. So let's do the problem above, except include a B field in the Z direction and make our bead charged with charge Q. So once again, we have our hoop. Now we'll have a B field in the Z direction. And it'll be uniform in space. We have our hoop. Now, what we need, remember, is to include a term m in our Lagrangian, where m of r and v is equal to q times v dot a of r, where a is the magnetic vector potential, and t. I should say m can also depend on t. Okay. And to make this work, I'm going to need to find the magnetic vector potential, which, remember, is not unique. It is any function or any vector field that satisfies del cross A is equal to B. In this case, the correct choice, these choices are also called gauges, but that's not really necessary for us. In any case, the correct choice is what's called the symmetric gauge, which is to put A in the phi direction. Now, I'm not going to work out all of the details right here, but what we can pick is A is equal to, well, we have a half that comes outside, and then B, which is our constant strength of the B field, and then we get a minus yx and 0 in the Z direction. And let's just really quickly check that that works. So if we do del cross A, we know that what we need to do is take our cross product of A, where the first vector in the cross product is the vector of partial derivatives. So it's like the determinant of x hat, y hat, z hat, delta x, delta y, delta z, and then minus y x 0. And I'll put my constants up on the right, half b. Okay, so in the x direction and the y direction, I'll let you check you don't get anything. And then in the z direction, I look at this component and then this minor, and I get partial x of x, that's 1, minus partial y of y, that's also 1, so I get 2. So this gives me back b. This all works out. Good. Now, this is also expressible as 1/2 b minus y x hat plus x y hat. And I could go and show that in cylindrical coordinates, this thing is exactly 1/2 b rho phi hat, which is pretty neat. Okay, so now what is my m term in this case? So m will equal, so just to be clear, this has charge q and mass m. So m is q times r dot, we'll get to that in a second, dot 1/2 b rho phi hat. Okay, that means that I just need to find the phi coordinate of r dot, because I'm dotting it into, taking the dot product, with a phi hat parallel vector. So what do I have here? R dot has phi hat coefficient rho phi dot, which is, in our case, rho times omega. Okay, so this is now q times rho times omega times 1/2 b rho. Or just to group this and make it less goofy looking, 1/2 b rho squared omega q. I think maybe the q should come earlier. 1/2 qb rho squared omega. Good. All right, now I want m, just like everything else in my Lagrangian, to be in terms not of the regular cylindrical coordinates, but in terms of my generalized coordinates. So I need to put it in terms of theta. But that's not so bad. I just need to express it in terms of rho. Okay, so r sine theta. So r squared sine squared theta. And let's pull the omega in there somewhere. All right, now let's take a look at the Lagrangian and see that something kind of interesting happens in this case. So mostly it's just exactly the same stuff that we had before. That's fine. But then with this extra term, but I want to note that there's a huge similarity between these two terms here. In fact, both also share this r squared. Let's note that. Now, if I pulled this last term into the parentheses here, that would mean that I had taken out a 1/2 mr squared. I got the 1/2 and the r squared there, but I would need to pull out an m. So I get qb over m times omega times sine squared theta, and then I'll add my term that I had before, omega squared sine squared theta plus mgr. Okay, but this quantity is really interesting. This one we have met before early on when we dealt with cyclotron motion. This is the cyclotron frequency. In other words, it's the frequency that a charged particle will orbit in if it's placed in a magnetic field. All right, and a uniform magnetic field. So this is pretty interesting. We get 1/2 m r squared theta dot squared plus omega times omega plus omega c sine squared theta plus mgr. Okay, what happens to our equations of motion? Well, our theta dot del d theta dot term doesn't change at all. In fact, the only thing that happens is our centrifugal term seems to change just a little bit. So in the end, we get the same equation, but with this omega squared replaced by omega plus omega c times omega. So that's pretty interesting.
Welcome back. Now we're ready to take our notion of generalized coordinates a little bit further even. Notice that in this first example, our problem had a nice symmetry to it, the fact that the spring didn't care about what direction you stretched it in. Similarly, in the problems that we did on the computer, we found that we had a nice cylindrical symmetry going on. So maybe there's some way that we can use generalized coordinates to express that symmetry. And in fact, there is. Now, we'll see right here that the coordinates phi and theta in this problem are both what's called ignorable. Let's give a definition. So an ignorable coordinate for Lagrangian L and I'm going to say that L depends on Q1 through Qn, Q1 dot through Qn dot. So this is the particular set of generalized coordinates that we have. An ignorable coordinate for this Lagrangian is 1, which does not appear in L, although its first derivative may appear. All right, good. So in this case, let's check r, theta, and phi, just to be as clear as possible. Notice that r does appear here, but theta and phi, and theta appears here, but phi does not appear here. All right, let's see what that entails. Well, if phi is ignorable here, then let's write our Euler-Lagrange equation for phi. We'll have that dl d phi is equal to the time derivative of dl d phi dot. But this side is 0 by assumption. Which implies that dl d phi dot is equal to a constant. Good. All right, so what happens in this case is the following. If I take that derivative, that's going to make me bring this 2 down and cancel the half. So I will get dl d phi dot is equal to m r squared sine squared theta times phi dot. And that object is a constant. Good. Now, why is it helpful to determine ignorable coordinates? Let's look at the Euler-Lagrange equation for r to figure out what we might be able to get out of defining this constant. So notice that this thing is going to be some constant. Let's call it curly L. All right, so for r, we have dl dr. Well, r turns up here and here. So we'll get m times r times theta dot squared, then plus mr sine squared theta phi dot squared. Good. And then minus kr. All right. Then we have dl dr dot. Well, that only turns up here, so that's just mr dot. So in the end, we get mr double dot is equal to mr theta dot squared plus mr sine squared theta phi dot squared minus kr. Now, the idea here is that anywhere that phi dot appears, we know that it's related in some nice way to a constant. And so it might behoove us to re-express this to get rid of phi dot entirely. And I must stress this, after we've solved the Euler-Lagrange equation. We're not allowed to do this in the Lagrangian. We're only allowed to do it in the Euler-Lagrange equation. Okay, so what would that give us in this case? We would get mr theta dot squared plus, actually, let me go ahead and rewrite this just to make our lives easier. So here, from these two equations, we would get phi dot squared in terms of L is equal to L squared over m squared r to the fourth sine to the fourth of theta. Great. Okay, so now we get theta dot squared there. We get mr sine squared theta. Then for phi squared, I'll just put in this expression I just wrote out down here. L squared over m squared r to the fourth sine to the fourth of theta minus kr. And we can do a little bit of simplification as well. Mr theta dot squared plus, we'll notice that the sine squared will cancel with some of those. The m will cancel with some of those. I'll get L squared in the numerator, and then m r cubed sine squared theta minus kr. All right. Now, what have I done? I've taken my Euler-Lagrange equation, which originally was an equation that was highly coupled. So it was one equation in a set that's going to couple r double dot with theta dot, theta, phi dot, and r. So these equations can get quite complicated. However, for every ignorable coordinate we find, we're able to eliminate 1 degree of freedom in our equations. And this can be really, really helpful because this equation now only depends on r theta dot squared theta, and that's it. There's no phi dot in the equation at all anymore. But this example is maybe a little bit more complicated than we need to see what some of our constants of motion that we actually find in problems really are. So I'm going to erase the board, and then we'll do a couple of really specific examples to get a handle on some things. All right, without further ado, let's look at some Lagrangians that have ignorable coordinates and see if we can figure out what their conserved quantities are. Remember, for every ignorable coordinate in a Lagrangian, there is some conserved quantity, namely the constant that we find on the other side of the Euler-Lagrange equation. All right, so first example, very simple. Let's just do 1D free particle. All right, the Lagrangian here is just 1/2 mx dot squared. Good. Now notice that because x doesn't appear, x is an ignorable coordinate. What does that mean for the Euler-Lagrange equation? Well, we would get d dt of the derivative with respect to x, which is mx dot, is equal to the derivative with respect to x of the Lagrangian, which is 0. In other words, this tells us that mx double dot, in other words, this tells us that mx dot is equal to a constant. What is this constant? This constant is the momentum. Notice this is m times v, exactly the momentum we expect. So what this tells us is that we have conservation of momentum when we have what's called translational symmetry. So one way that we can state that a coordinate is ignorable is that our Lagrangian has a symmetry with respect to that coordinate. The idea here is that if I change all my points, x, to points a little bit further down, say x plus 1 meter, then this Lagrangian doesn't change at all. And therefore, we have a translational symmetry here. If we translate all of space by some amount, the Lagrangian is left invariant. And that leads to conservation of momentum. Okay, so let's actually state that as a rule here. And let me, just to be really clear here, make sure that it's obvious that I mean linear momentum. All right, let's do another example. Okay, let's do the same example as before, but in 2D. So we'll do 2D mass on a spring. Here, I'll use polar coordinates rather than spherical coordinates. Okay, so my Lagrangian is 1/2 m times the r dot vector squared, but you can go back to our video on polar unit vectors to see that that is given by r dot squared plus r squared times phi dot squared, and then minus 1/2 k times r squared. Great. Now in this case, we have that phi is ignorable, just as we did in 3D. All right, so let's write our Euler-Lagrange equation for phi first. In this case, or maybe we don't even need the whole Euler-Lagrange equation, but we just need this object. This object, dl d phi dot, in this case is mr squared phi dot. Good. And once again, we'll call this curly L. Now, this is a good time for an aside in which I'll give another definition. Anytime we have a coordinate, we can call dl dqi the generalized momentum. Maybe use colon there. Generalized momentum for qi. So in this case, dl d phi dot is the generalized momentum for phi. All right. And this is the thing which is equal to L, this constant. Okay, now I can stick that into my Euler-Lagrange equation for R. Let me start deriving that. So dl dr dot is mr dot. dl dr is equal to mr phi dot squared minus kr. All right, just like before, I need to find phi dot squared in terms of L and R and substitute it in here. So I get the following Euler-Lagrange equation. I get m r double dot is equal to m r. Now phi dot squared is going to be L squared over m squared r to the fourth minus kr. Okay. Now canceling everything out on the right-hand side, I get the following. And from this expression, if you've seen something like this before, you know that L here is the angular momentum. This term would then be called the centrifugal term if you want to think of it as a force. You may have seen that in introductory physics. But in any case, what we found is that in this example, the ignorable coordinate was phi. That means that if we rotate our system by some angle and re-express the Lagrangian in the rotated coordinates, the Lagrangian is going to be exactly the same. So this system has rotational symmetry. So rotational symmetry is 1-to-1 with conservation of angular momentum. All right, now I could keep going on and figuring out new Lagrangians with ignorable coordinates and naming new kinds of generalized momenta that are being conserved in those cases. But the general principle holds. Anytime we have an ignorable coordinate, we can also express that as an invariance or a symmetry, translational symmetry or invariance here, or rotational symmetry or invariance there. And we find that in each case, we get a conservation associated with that symmetry. Now, I want to deal with a case where we can't express things in terms of generalized coordinates, but we do still see a link between symmetry and conservation. And to do that, I'm going to need to introduce a new entity. Let me call this entity curly h. Now, curly h is equal to a sum over all the generalized coordinates of the time derivative of the generalized coordinate times the generalized momentum for that coordinate and then minus, outside of the sum, the Lagrangian itself. This construction may seem a little odd. In fact, this construction is the Legendre transformation, which you may or may not have encountered before. It is very interesting, but I'm not going to discuss it anymore here. I'll suffice it to say that H will become clearly important as we continue our discussion, just through examples and through the proof that I'm about to do. All right. In any case, this object H is called the Hamiltonian. And as I said, through an example, we'll get to see what the Hamiltonian really is in most mechanical systems. But first of all, I want to do the following. I'm going to show that if the Lagrangian does not depend on time, then H is conserved. Okay, so if, and only if, L does not depend on time, H is conserved. And really, to make this the if and only if, I would have to say H is only conserved for all starting conditions if L does not depend on time, but you can fill in those details if you'd like. All right, let's go ahead with the proof. All I'm going to do is take the time derivative of H explicitly. All right. Now to do that, we're going to need to just go term by term. So inside of the sum, things are not too bad. All I need to do is use the product rule. So in the first term, I get qi double dot, then dl dqi dot. In the second term, I get qi dot times the time derivative of dl dqi dot. And I'll just leave it like that. Next, I'll need to take the time derivative of the Lagrangian, but this is the total time derivative. And so I need to think of the Lagrangian as really being composed with the following vector. It's the vector of all of the qi's so qi through qn, sorry, q1 through qn, I should say. Then all of the qi dots, so q1 dot through qn dot, and then t, although we know that our Lagrangian does not depend on t. Now, if I do this composition, then what I really need to do is take the chain rule, the multi-dimensional chain rule. What this is going to tell me is that every time I want to take a time derivative, or if I want to take a time derivative, I need to take the derivative of L with respect to each of its coordinates, and then multiply the derivative of that coordinate with respect to time. All right, so let's do that explicitly. First, I'll take the time derivative, or the derivative of L with respect to each of the generalized coordinates themselves, not their first derivatives. And from that, I'll get a dl dqi, dqi, then the derivative of that generalized coordinate with respect to time, so times qi dot. Next, I'll take the derivative of L with respect to each of the first derivatives of generalized coordinates. So that'll be dl dqi dot times the time derivative of each of those coordinates. So that's qi double dot. Good. All right. Next, I need to group my terms. So what I'm going to do is notice that my qi double dot terms cancel. So that and that cancel. Notice that this one has a positive sign, that one has a minus sign, but otherwise they're the same. Then I'll notice that both of my remaining terms share this factor qi dot in common. All right, so I can pull that qi dot out. Then I get d dt dl dqi dot minus dl dqi. But notice that this thing is equal to 0 by the Euler-Lagrange equation. Now, for all of this to work out, I needed that this partial derivative of L with respect to its last coordinate, t, was 0. I can put a minus 0 here just to remind myself that that was true. Otherwise, I would pick up another term here, and that would break the whole thing. So, because the partial derivative of L with respect to t is 0, I get that the time derivative of h is equal to 0. So h is some constant. But what is that constant? What, in this case, do I get? Well, let's look at an explicit example. Let's let L be half m times r dot squared minus, and let's just do this in rectangular coordinates, actually. So let's specifically say that this is r1 dot squared plus r2 dot squared plus dot 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 plus rn dot squared. So this is rectangular coordinates, but in any dimension. And then we'll say minus u of r1 through rn. In other words, the only thing that I'm specifying here is that we have a time independent potential. Wonderful. Okay, so clearly this term does not have any t dependence, and this term has no t dependence. So this is a time independent potential, and that means that there's no t in here. All right. Now, in this case, what is h? Well, what I need to do first is figure out what the generalized momentum dl dr I dot is. In this case, the generalized momentum is just the linear momentum, mri dot. Wonderful. So H is now equal to the sum over I of MRI dot times RI. So let me express that as MR1 dot squared plus MR2 dot squared plus dot 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 plus MRN dot squared minus the Lagrangian, which is 1 half times M times R1 dot squared plus dot 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 plus Rn dot squared. Now this minus turns to a plus because we're subtracting the Lagrangian here. So plus U of R1 through Rn. All right. Now notice that each term here appears over here as well, except attached to a minus 1 half. So in the end, we get 1 half M times R1 dot squared plus dot 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 plus Rn dot squared plus U of R1 through Rn. But notice that this is exactly the kinetic energy plus the potential energy. In other words, this is the total mechanical energy. Now, before I continue, I need to make a couple of careful caveats. The first is that this is the total mechanical energy unless I have the magnetic term in the Hamiltonian, or in the Lagrangian, I'm sorry. The second is that even though the Hamiltonian can always be defined, there's nothing that says I can't write this even if the Lagrangian depends on t. It's only going to be conserved when I have no t dependence. All right, but this gives me my last conservation that I wanted to point out, which is that if I have time translation invariance or time translation symmetry, that is one-to-one with conservation of mechanical energy. Now, as it turns out, in a few weeks, we'll have reason to revisit the notion of the Hamiltonian and of these generalized momenta. But for now, all we need is that this is part of the constellation of relationships between symmetries and conservation. Now, I want to cap off this video by talking about one other really powerful technique from Lagrangian mechanics before we move on. I'm going to hop to the computer to do that.
To wrap up our discussion of the various machinery available to us in the Lagrangian formalism, I'm going to talk again about constraints. Now, we've already talked about the fact that I can restrict my attention to the constraint subspace, come up with generalized coordinates for that subspace, and then use those generalized coordinates in my action and solve the Euler-Lagrange equations. But sometimes finding generalized coordinates on a subspace is very hard, or maybe what we get is just really gnarly. Maybe there's some other reason that we don't want to proceed in that way. If we want to remain in rectangular coordinates, there is another way that we can incorporate a constraint, in specific a holonomic constraint, into our problem. And that's the method of Lagrange multipliers that we're going to focus on today. Okay, so I am going to hop over to OneNote, and the first thing I want to do is just look at how this works in practice. So let's start with an example. The example we'll look at is just a pendulum. Okay, so this will have mass m, length L. Now we know that the equation that we get here is theta double dot is equal to minus sine of theta times root g over L. Good. If this angle here is theta. And you can go back to any introductory textbook which will derive this. I'm going to just assume it, and then we'll try to see if we can get to it using Lagrange multipliers. All right. Now, how does this work using Lagrange multipliers? Well, what we're going to do is the following. Notice that our Lagrangian for this problem, if there were no constraint, would just involve this one single mass moving in 2 dimensions. So we would have 1/2 m times x dot squared plus 1/2 m y dot squared minus mg times y. But we also have a constraint. In this case, it is a holonomic constraint, which is what we want if we're going to use this method. And the constraint is as follows. We need that x squared plus y squared is equal to L squared. Or if I want to talk about the constraint function that I've used before, I can have k of r is equal to 0, where k of xy is equal to x squared plus y squared minus L squared. Good. Okay, so the Lagrange multiplier method is going to involve amending this Lagrangian, changing it in a specific way. I'm going to rewrite a new Lagrangian, or I should say write a new Lagrangian, which is the old Lagrangian minus a function lambda. So lambda is going to be a function from the reals to the reals, and lambda is going to take in time. So it's a function of time just like x and y are. And then times my constraint function k. And the claim is that by minimizing this function, or by finding the stationary point of this Lagrangian, I can solve my original problem for some lambda. So let me write it like this. There exists lambda. And actually, just to match the notational convention in the textbook, I'm going to change this to a plus sign. Because we're just saying this exists for some lambda, it doesn't matter whether or not I put a plus or a minus here. Okay, there exists some lambda from the reals to the reals, such that solving the Euler-Lagrange equations for, let me say, x, y, and lambda produces, but with no constraints, I should say, with no constraints, produces the correct trajectory. All right, now let's see if we can prove that that is what in fact happens for the case that we're interested in. Here, what we'll have is okay, so in the example, L lambda is 1/2 mx dot squared plus 1/2 my dot squared minus mgy, and then plus lambda times x squared plus y squared minus L squared. All right, so what are our Euler-Lagrange equations? Let's do the lambda one first, because I think it is the most, the simplest to see, I should say. In this case, we have dl lambda, d lambda is equal to x squared plus y squared minus L squared. And dl of lambda, or L lambda, d lambda dot is equal to 0. So this implies that x squared plus y squared minus L squared is equal to 0. And that's exactly our constraint. Great. Next, let's get our equations for x and y. So for x, we'll get dl lambda dx is equal to, well, that's just 2x lambda. Meanwhile, dl lambda dx dot is equal to mx dot. So the Euler-Lagrange equation we get here is mx double dot is equal to 2x lambda. Good. Then for y, we get dl lambda dy is equal to 2y lambda minus mg. Meanwhile, dl lambda dy dot is equal to my dot. And that implies that my double dot is equal to 2y lambda minus mg. All right, let's make a couple of small simplifications. So the first thing that I want to do is take lambda, and I'm going to replace it. I'm going to make a guess that lambda here is negative. And because of units, I can say I'm going to try and replace it by minus m times omega squared, where omega is some function. Now I say because of units or dimensions, because I know that the dimensions of lambda ought to be mass over time squared. So something like omega seems like it works. All right, now let me star the equations that we actually come up with from this. I'm going to slightly reorder them. So for the x, we'll get, actually, the m's will cancel. So we get x double dot is equal to minus omega squared times x. For y, we'll get y double dot is equal to minus, oh, and sorry, I should have had minus m omega squared over 2. Good. Okay. Anyway, for y, we'll get y double dot is equal to minus omega squared y, and then minus g. Good. And then finally, we'll get x squared plus y squared is equal to L squared. Great. Okay, now it seems like this looks exactly like a spring equation. But it isn't, because omega here is not constant. Omega is a function of time. And so we can't use our normal methods for solving second order ODEs with constant coefficients here. Now, there are a variety of ways we could go about trying to solve this system of equations. One of them is that we could move to polar coordinates and try and solve there, but I'm going to take a slightly different approach. I'm going to start taking derivatives of my constraint equation. So the first thing I get is 2x x dot plus 2y y dot, y dot is equal to 0, or in other words, x dot plus y dot is equal to 0. And then I'm just going to do it again. So I'll get x dot squared plus x double dot plus y dot squared plus y double dot is equal to 0. Okay, now I'm going to reduce the order of this by taking all of my x dots and y dots and replacing them with what I have from here. Okay, so just showing the implications here. I'll have x dot squared plus, and I guess I should actually change that to minus, omega squared x squared plus, okay, and then y dot squared, then minus omega squared y squared. And then what do I need to do next? I need to take this this g here and replace it. So minus g times y, and that is equal to 0. Now I'm going to rearrange terms just a little bit. Okay, so I get x dot squared plus y dot squared minus omega squared x squared plus y squared minus gy is equal to 0. But notice that this thing itself is L squared. So x dot squared plus y dot squared minus omega squared L squared minus gy is equal to 0. And now we're in a pretty good position because we really can move to polar coordinates, and we have a much simpler equation to deal with. Okay, so I'm going to deal with polar coordinates such that if this is x and this is y, I'm actually going to define phi to be this angle here, so that x is equal to r sine phi and y is equal to minus r cos phi. That implies that x dot is equal to r dot times sine phi plus r phi dot times cos phi. And y dot is equal to r dot minus r dot, cos phi plus r phi dot sine phi. Okay, so now I'm going to take those expressions and square them. I'm going to get r dot squared sine squared phi plus, now the cross term here, 2r dot times phi dot times cos phi sine phi, then plus r squared phi dot squared cos squared phi. Okay, that's my x dot squared. Now my y dot squared, I get r dot squared cos squared phi. My cross term minus 2r dot cos phi sine phi. And then my last term here is my r squared phi dot squared sine squared of phi. Okay, now I still have my minus omega squared L squared minus g times y, but that's plus r cos phi. But check it out, I get tons of cancellations here. This term cancels with this term, and then this term and this term can be combined, and this term and this term can be combined using the Pythagorean identity. So after a bit more simplification, I get r dot squared plus r squared phi dot squared is, minus, and I forgot my equals 0 here, minus omega squared L squared plus gr cos phi is equal to 0. But it gets even better. Because I have that x squared plus y squared is equal to L squared, I also have that this implies that r squared is equal to L squared. Or because r must be positive, r equals L. But then r dot must be 0, and everywhere where I see an r, I can change it to L. Okay, so this term is 0. Then I get L squared phi dot squared minus omega squared times L squared plus GL cos phi is equal to 0. Okay, almost done. So now I can cancel one factor of L. In fact, I'm going to just divide by L squared. So I get phi dot squared minus omega squared plus G over L cos phi is equal to 0. Okay, the issue here is that I still don't actually know what omega is, but this is going to allow me to solve for omega in terms of things that I do know. So in particular, this lets me say that omega squared is equal to, well, if I move it to the other side, it's phi dot squared plus G over L cos phi. Okay, let me box that equation. And the reason I'm boxing that equation is because now I'm going to go back to my original equations. Okay, let's go back to my original expression for x now. I had x double dot was equal to minus omega squared times x. Now what I'm going to do is solve, as I had before, for x in terms of r and phi. Here, however, I know that r, again, is going to be just L. So that means it's going to be pretty easy to take my time derivatives now that I've figured that out. Okay, x dot is just going to be what? L phi dot times cos phi, and x double dot is going to be equal to L times phi double dot times cos phi minus L phi dot squared times sine phi. All right, so at long last, I can put my equation together. Okay, I have L phi dot cos phi minus L phi dot squared sine phi is equal to minus this quantity, phi dot squared plus g over L cos phi times L sine phi. Now immediately I see that an L cancels on both sides. I also see that I have a minus phi dot squared sine phi on the left-hand side and a minus phi dot squared sine phi on the right-hand side. So I can cancel those. Now everything just depends on something that's a multiple of cosine of phi. So I can scratch out my cosine of phi as well. And at long last, I get phi double dot is equal to g over L times sine of phi with a negative sign, making me realize that way, way, way back at the beginning of the video, I put a square root here when I shouldn't have. Sorry about that. Okay, so this works, although in this case, it was much harder than the way that we already knew how to do this. Okay, but at the very least, it works. So why does it work? I'm going to answer that question in 2 stages. The reason I'm going to do that is that the formal general proof is actually pretty complicated. But it turns out that this method, Lagrange multipliers, is not constrained to calculus of variations. It works in regular calculus as well. So let's imagine we're trying to maximize an ordinary function in 2 dimensions. So f from R2 to R, subject to a constraint that g, which is also a function R2 to R. So let me say that g of x, y is equal to 0 for some function g that goes from R2 to R. Okay. Now, to be really super specific, I'm going to work an example as I do this problem, or as I sort of talk through the mathematics. So in my example, I'm going to let f of xy be equal to x squared plus y squared. I said we're trying to maximize something. It could also be that we're trying to minimize something. Let me just say, instead of maximize, extremize. Find the stationary points. All right. Now, what do the level curves of this function look like? They look like this. So this is level curves of f. I'm going to let g of xy be equal to x plus y minus 1. Okay, so g of xy equals 0 means that we're looking along the line. So let me say this means that the constraint subspace is the points x and y satisfying y is equal to 1 minus x, just by a rearrangement. Okay, so my constraint subspace is just this line. So I know exactly how to extremize the function along this line. What I'm looking for is this point. The question is just how to exactly find that. Now, I can think of a number of different methods. I mean, maybe the simplest one is just to find some coordinates on this space, or coordinates for R2 that fix such that in those coordinates, there's a fixed value of the coordinate along this blue line. So for instance, we could define, so method 1, let u equal x plus y minus 1. And then for v, we can just, for instance, pick y. All All right. That these two together imply that x is equal to what? It's u minus y plus 1, but that's u minus v plus 1. And then y is equal to v. All right, so now x squared plus y squared is equal to u squared minus 2uv plus v squared plus 2u minus 2v plus 1 plus v squared, or is equal to u squared minus 2uv plus 2v squared plus 2u minus 2v plus 1. Okay, now I'm only looking at points where u is equal to 0 by construction. So note, u equals 0 is the constraint subspace. Oops. And so I'm just going to set u equal to 0, and then v is going to be the coordinate that moves me within my constraint subspace subject to u equals 0. Okay, so x squared plus y squared subject to u equals 0 is equal to is equal to 2v squared minus 2v plus 1. All right, now I want to maximize this function or minimize this function in this subspace. I'll just take a derivative of this thing. So the derivative with respect to v of 2v squared minus 2v plus 1 is equal to 4v minus 2. I want that thing to equal 0. So that implies that v should equal half, which in turn implies that y, so maybe I should say it implies y is equal to 1/2, which in turn implies that x is equal to 1/2. And that's exactly what we expected. This is the point here, 1/2, 1/2. So the method that I just did, method 1, is analogous to what we did in Lagrangian mechanics, in which we found coordinates on the constraint subspace, generalized coordinates on the constraint subspace, and then we just did our variational calculus in those generalized coordinates. Those generalized coordinates are like u and v. Method 2 is going to be the method of Lagrange multipliers. Now, this basically all rests on a really important claim. So, claim, I need to have, so for the point, let me call the point that is the actual point that I want, x naught, y naught. Let's call this point x naught, y naught. So for the point x naught, y naught, I must have that the gradient of f evaluated at x naught, y naught is proportional to, or is parallel to, the gradient of g at x naught, y naught. Okay, let's do the proof by contradiction. Okay, so suppose that this is not true. So it's not parallel to the gradient of x naught, y naught. Then there's a direction that I can go that increases f, but keeps g the same. Now, I think it'll be a little bit easier to see if I go here and start looking at what happens. So for instance, let me give myself another color. Sure. Let's assume I'm at this point. Now the gradient, remember, points in the direction of steepest ascent. So the gradient of f points in this direction at this point. But the gradient of g, because g is a sort of linear function in these coordinates, the gradient of g is always in exactly this direction. All right. Now, that means if I want to minimize f, if these aren't parallel, if I move this way, I'm going to decrease f while keeping g the same. So if I'm trying to extremize f, I can change f while leaving g the same by moving in that direction. All I need to do is put a slightly more formal language to that, but that's really the intuition here. Okay. So what I'm going to say is there exists w, let me say there exists a vector w such that the directional derivative in the direction of w of g at x naught, y naught is equal to 0. Maybe actually, I guess it should be here. Good. But w dot the directional derivative in the w direction of f is non-zero. So we can change f without changing g. Then x naught, y naught cannot be extremal. Okay. So one really important point to stress here, by the way, is that I was assuming that the point x naught, y naught is in the constraint subspace, right? So if I'm in the constraint subspace and I don't change the value of g, then that means if I started with g is equal to 0 at that point, then along this curve, g stays 0. And that's why this whole thing works. Okay. So the only place that I can go such that the gradient of f and the gradient of g become equal is exactly this actual point x naught, y naught, where, as you can see, they will both point up and to the right at a 45-degree angle. Okay, so let me say this is like the actual point here. Or it's proportional to gradient of g. All right, so now what does that mean? We have that gradient of f. So gradient of f is proportional to gradient of g, or gradient of f is equal to minus lambda gradient of g, where lambda is going to be our Lagrange multiplier. All right, so if I move this all to one side, I get that the gradient, so here, by the way, lambda is just a real number. That's important. Okay, so I have that the gradient of f plus lambda g is equal to 0. And so this is my analog of the Lagrange multiplier approach. In calculus of variations. All right. So now I've given a relatively complete proof of why it works in this setting. There is one thing that I wanted to mention here before we move on, though, which is that, of course, there are many points that meet this constraint, namely all the points along this entire line. So I need a second constraint. In fact, I need this. So this can be the first equation that I need. And then I also need, that we're on the constraint subspace. G is equal to 0. And those two together are enough to give me a unique point and the correct point. Okay, so now let's move on to a slightly more intuitive argument for why this works for calculus variations. Okay, so let's go back to the action itself. Okay, so we have S of R, and that is equal to the Lagrangian, the integral, I should say, from Ti to Tf, of the Lagrangian of R dot, and T, dt. And then I have a holonomic constraint. So again, I have K of R is equal to 0. Let's just do a single holonomic constraint for the time being. Okay, so the way that I am going to implement this is to amend the action like this. So we'll have Lagrangian as before, and then plus lambda K of R dt. Now, taking the analogy too much further would take us really deep into calculus of variations, which I don't think is probably worth it. But let me just talk us through a little bit of what's going on here. So there are some variations, so maybe I'll just write this out in words. There are some variations phi which we can take, or which we can add to a trajectory R naught that does satisfy, or that satisfies, K of R naught is equal to 0. So in other words, for all t. So in other words, if we start with some trajectory that is on our constraint subspace, that's a lot like this green point that was on our constraint subspace in the original, or in this finite dimensional case, then that's analogous to this R naught. We can start with something that's there. Now, it will typically be the case that there's a direction that we can go that leaves us within the constraint subspace, but does affect the value of our function f. Or down here, there's a variation that we can do that affects the value of s. Okay, so let me say most of the time, there is a small variation that does not kick us out of the constraint. Maybe I should say such that adding it does not break the constraint, but doing so changes s, i.e. K of R naught plus phi is still equal to 0, but S of R naught plus phi is not equal to S of R naught. But if we find the correct R naught, then any variation that changes phi, that changes S also breaks the constraint. And that is what the Lagrange multiplier sort of encodes. It encodes that when we found the correct R naught, then the variation, any variation that we can do is also going to break the constraint. And it encodes it in the exact same way as it did up here, just with slightly fancier functional calculus. All right, there's a little bit more that we could say about Lagrange multipliers, namely that they also encode constraint forces. So I'll say that and then I will end off. So last point, Lagrange multipliers encode constraint forces. All right, so to see that actually, we can just go back to our original example with the pendulum. Remember there are equations where m times x double dot is equal to 2 lambda x, and my double dot is equal to 2 lambda y minus mg. All right, what's going on here is that mg, remember, is the unconstrained force, or maybe I should say the conservative force here. But in order to keep the pendulum from just falling with constant acceleration downward, there must be a force keeping it up. And that force, in fact, is the force of tension. Okay, so right, if we did this in our sort of physics 101 way, we would say that we have these two forces on our mass, and then we could actually figure out what this force of tension is. And in fact, what we would figure out is that it has exactly the form that's correct to be this. So this is in fact just the x component of tension. And this is just the y component of tension. And since tension changes, that is why lambda needs to be a function of time. All right, so hopefully you've seen that the method of Lagrange multipliers can be really helpful. And that's going to wrap up everything that I want to say in a sort of very general sense about using Lagrangians. We're now going to hop into the most sort of traditional or the most classic case for using Lagrangians, which is in problems in which we have two bodies and they're exerting central forces on each other. This is, of course, what Newton and all of his colleagues were very interested in to begin with. All right, thanks for watching this one, and I will see you in that video.